So that's what this paper is about. So let me tell you about first for this. Who's here? So Penn was a student of mine many years ago. She was at Bill Kent University. She's on leave from Bill Kent in Australia, in Sydney, and probably go back. Well, she'll be an academic anyway. Esma is currently on the market, and Esma ran the experiment that we used. Esma is really great. So, Okay, so, when you take an exam, most of the time, there's a lot of time pressure, right? You've got 3 hours to do the exam, and you just don't think about anything but doing it. And there are lots of these instances, auctions, buying, selling stocks, contests, all this time pressure. And rankings in these exams depend on the ability to perform under pressure. So what we do is we see how performance is affected by time pressure and how this varies across ability of the agent, the difficulty of the question, gender in multiple choices. Why gender? Because in the education literature, there's this big preconception that women don't do well under pressure and they're not as competitive and more risk averse than men. Okay? I'm going to show you, I hope convince you that the evidence is not there, that they've been misinterpreting the data. So a lot of exams are like this, the SATs. The SATs try to rank all students in terms of college applications. There's another exam called the American Math Applications. These are to identify students with very good math background. The median, this is given in high school, and the median score is 0. Okay, they're really trying to find those few students who can think like a mathematician. Right? And this is important because if you think about what we expect, it is that the best students will gain the most from being given the most opportunities. So there's some complementarity between ability and resources that you will give to them, which is why you want to place the best students in the best places, in the best universities. That's why Tokyo will get the best students, because the best students will gain the most from being in Tokyo. So we did this by using an experiment. So we conducted the experiment in a Turkish high school, and the senior high school students were randomly allocated to 2 groups. One group was the treatment, the existing time constraints, and the other was, the new time constraints, and the other was the control, the existing time constraints. And they took, the mock entrance exam with different time. And in contrast to all of the literature so far, we actually study these results of this experiment, both in terms of reduced form effects, which is commonly done, and through the lens of a structural model. And our structural model is completely new. In the literature on education, there is no model that says, this is how a student approaches a multiple choice exam. And this is what the components of this model are. So we have a previous paper where we build this model, but with no time constraints. And so here we extend that paper and use the data, the experimental data, to estimate a structural model, a static structural model, much simpler than in the last paper, to understand how to think of the reduced form results. Okay? What should we take away from there? So, you'll see that the factors that are going to influence decision-making as to how to answer the multiple choice exam are going to depend on what? Ability, If you're more able, you're going to be able to spot the right answer better and so get a higher score. If you're less risk averse, you'll be willing to guess more. And as long as you're guessing so that your expected gain is positive, guessing more is a good thing for your score, right? So, if you're more risk averse, your expected score will be lower because you should have guessed, but you didn't guess. Okay? We're going to find that when you have higher ability, higher time, more time, easier questions, you're going to be more likely to get the right answer. How we model this is, I think, pretty novel. Right? There's this big thing, preconception in the literature that, women are less confident or more risk averse than men. Okay? And in this paper, we're going to show that it's not that easy to separate risk aversion and confidence. Right? Both of them will have the same consequences on whether you attempt a question or not. If you're not confident, then you'll say, oh, well, I must be wrong, I won't answer. If you're risk averse, you'll say, I could lose a lot if I get the wrong answer, and so I won't answer. So the consequences will be the same. So it'll be very hard to separate these two out. But risk aversion is a primitive. That doesn't change because you have more time. That's inherent to you. It's the shape of your utility function. That doesn't change because you have more time. But your confidence may change because you have more time. Because I have more time to look at the question, I can think more, I can be more confident. So if you see this risk aversion plus confidence estimate changing with time, it has to be because you become more or less confident. That's how we separate risk aversion from confidence. In the literature, they usually add some sort of survey that gets you risk aversion, and then the rest is confidence. But we don't need to do this because it's a primitive. We're fine. Okay. So,
I may think, hyperbolic discounter, they skip the question easily to procrastinate.
Yeah.
So
this is a paper exam, so you can always come back. So it's very hard
so
to.
within the time, they should
they could come back.
Make a decision anyways. So hyperbolic discounting or
it's not going to happen. It's a very good question. So we're going to look at, after estimating the model, we're going to explore, counterfactual simulations. Does giving you more time make, you'd say, okay, if women are less confident than men, it's not risk aversion, that's different. If you give more time, you should expect the women's confidence to improve faster than that of men. So you'd expect this gender gap to be closed more when you give more time. We find the exact opposite. Okay? And I'll explain why that's happening. Okay? To give away the entire paper, the reason is that the production function, signal production function, is different for men and women. And because it's different for men and women, you can get the women having more disadvantage with more time than men. And it's very clear from our estimates that it's not risk aversion. It is the fact that women and men are processing these signals in different ways. And this is in line with what the psychology literature suggests, which is the way that by gender, you process things like women are supposed to be able to figure out where they are in a different way than men. Women say, okay, come to the corner where you'll see the petrol station and turn left. Men say go north and then go east. Okay. This is something in psychology where they claim that the minds just operate a little bit differently. And they have a lot of these examples to support this. And so the psychologists won't be surprised by our findings, but the economists will be. Okay, so this is basically what we do. So, there's a huge literature here that none of it is structural. A lot of it has, results which we think are maybe misinterpreted. So what we find in what's found in the literature is what you would expect. Accuracy falls with time pressure. Yes, that makes sense. You give you less time, you're not going to get the answer right. If I give you more time, maybe we'll find the right answer. Speed and accuracy are driven by a more informative signal. And your signal is more informative if you have higher ability. And the question's easy. So this is what you see in the data. Another literature talks about gender gaps in high-stake tests. And they say, look, women skip more than men. And that's why they score less. In many countries, not all, but most countries, you find women do better in high school than men. The psychologists say that's because women mature faster than men. And so, they're able to concentrate while the men can't concentrate. Well, okay. But by college, the men have caught up. And then in college, for the college entrance exam, the men do better than women. There's another reason also, which is women have an outside option, right? Like in India, what do you tell a smart girl who's lazy? You say, it's okay. If you're pretty, you will find you a nice husband. You don't have to work hard. You tell a smart boy who's lazy, you say, if you don't work hard, nobody will marry you. So the outside option is very different for men and women. And that might also be why women don't work as hard in the university entrance exams in these countries. So we're extending the literature by adding time constraints in the structural model. There's a lot of work that shows time pressure matters, but there's no paper that tries to explain how it matters and how it differs by gender. And that's our contribution.
There's a literature on orientation towards competition, and the women's are less favorable.
Yeah, but there's no model to look through the lens of to understand the different components. They just say, okay, this happened. So it's all reduced form.
Yeah, it is.
And so let me motivate what led to this paper. Okay, in Turkey in 2010, they almost doubled the time for the national university entrance exam. The number of questions was roughly the same. The difficulty was roughly the same. They increased the time about 80%. So there's data there, but the data is only at the school level. So it's not at the individual level. We wanted individual level data, which is why we did the experiment. So at the school level, this is what we scraped off the web. On 2010 score is on the y-axis, and 2009 score, the year before the change, is on the x-axis. What do you see? The 45-degree line is here. You see it's above the 45-degree line. You gave more time. The average score in the school went up. Okay? You see something else that's interesting. This is the fitted red line here. You see that it didn't change that much down here. It didn't change that much up here. It changed the most in the middle. So it's like a humped. Do you see that? This is what got us thinking. We said, why? And then it occurred to us, it's obvious. Down here, people are dumb. Schools are bad. Average student there, not so good. If you've got more time, it's not going to help you. Over here, the students are quite bright. You have more time, you don't need more time. This is where you're going to get all the action. And that's exactly what we thought was happening. And that is roughly what happens. What are the colors? Here the colors are just, ability is low, getting higher, green, then even higher in red, in blue. Here we plot the standard deviation in 2010 and the standard deviation in 2009. You're below the line, right? Standard deviation is going down. The variance is going down. Yes, that's what you'd expect. You're more certain of your answer, right? So this again made a lot of sense. But you see, the standard deviation for high scores, the colors are changed. It's yellow, low ability, then blue, high ability, and then green. So the standard deviation here is highest for the green guys, which again makes sense, right? On the bottom, you're not going to get much of a change in the standard deviation. Similarly, at the top, the most is over here. So this is just fun. Okay, so we replicate this natural experiment, right? And the main negative of our paper is this was the first time we'd done an experiment like this, and we didn't have a lot of money, so we only had 83 students. Esma, in her job market paper, did another experiment on something awfully interesting, which is cooperation versus competition. How cooperation might be affected by intense enough competition. And it's a super interesting paper. And there are 1,000 data points there. But this here, this is the most weak part of the paper. Just we didn't have enough. We didn't have enough money, and we didn't know how important this was going to be. So, half and half roughly in the treatment. There are 24 balanced males, females, and the control. We just broke the thing up. Again, randomized. And the balance check shows that all the same is known. So the multiple choice exam is designed in the following way. There's negative marking, and this is important. The right answer gives you 1 point, and the wrong answer deducts 0.25 points. And skip, you don't get anything, 0. And this is actuarially fair. So expected, you don't gain by guessing in terms of expected score. And there are a bunch of different quantitative.
Can I ask a question?
Yes, of course.
Is this exam incentivized?
Sorry, say that again.
Is this exam incentivized?
Is this what?
Exam incentivized? I want to understand.
Oh, yeah, we gave money. We gave money. We gave $30, which is a lot in Turkey at this time, to the students who were 1, 2, 3. Then $3 less for 4, 5, 6, and so on.
Nice.
So for them, this was pocket money. And Turkey has been having a really hard time because the economics is terrible. The government is not having good economic policies. The Turkish lira has depreciated by huge amounts, and real wages have been falling in Turkey. So this is a lot of money for the kids. Sorry, I forgot to.
So they worked seriously.
Sorry?
They worked on this exam seriously.
Yeah, they took things seriously. So, this is the time constraints. So it's roughly, twice as much time, as I said. And, the incentives, the top 3 were given about $30 and same, less for. That's about 10 hours of the minimum wage. It's not bad. They took it seriously, much more than people in experimental labs in the US would take. So, and you'll see, it shows in the data. You see scores increase on average, skipping decreases, and the treatment effect is highest for questions within reach. So this is again a novel thing for us, which makes sense, right? If I give you a question to answer, which you could get if you thought about it, you're going to have a large effect if I give you more time. If the question you already know the answer to, it's not going to make any difference. If it's too easy, it won't have an effect. If it's too hard, there's no way I'm going to figure it out. I just don't know the material. So the effects should be largest for questions within reach. That's exactly what we find. So here we are. These are the average treatment effects for fraction correct, wrong, conditional correct, skipped, and the score. Okay. This is the control, this is the treatment, and then this is the difference. And this is the p-value. So what you're seeing is, this goes up a lot. It's not from chance. Wrong. Well, it could be chance. Conditional correct. Well, things are operating in different directions. Which questions are you going to answer when you get more time? The ones you are the most doubtful about. So conditional correct could go either way. So it's not as clear. Skip, very clear. Right? You skip less. And score, very clear. You get a higher score. So everything that I told you, intuitively, you see. The fact that it was within reach that matters. This is the treatment effects as a function of question difficulty. Okay? So we divide the groups into below median ability and above median ability. We get ability on the basis of their scores in practice exams. This was run through the test cramming school. So low ability, the treatment effects peak much lower difficulty. This inverse U-shaped, again, which we expected. Here, it's not going to help time. Here, time is not needed. It's going to matter most for the questions which are within reach. For low ability, these questions within reach are much easier. High ability, questions within reach are harder. Males and females, the picture looks a little different. Right? It looks a little bit higher treatment effects for men. And this hump is happening a little bit further out here, which we're not getting. So it looks like men and women are different in terms of their responses. So how are they different? That's what our model is going to try and give you. It turned out that we also get more gender bias with more time. So instead of what we expected, that the women would catch up with more time, we get that the men gain more from more time than the women. So here we are. We're looking at this by gender. For correct, skip, you see, they're getting more correct. Men, they're skipping less, and the score is going up. Look at women, not so significant. Less significant than men. Okay. This one's borderline. Yeah. So they skip less. Men skip a lot less. Score change, more for the men than the women. This is exactly what I told you. We give you more time, and the men are gaining more than the women. Oh my gosh.
Yeah, this is very interesting. So when you compare boys and girls in this table, do you control for skills between them?
Just now, this is just an average.
So this could reflect some skill differences.
Yeah. It could be.
Okay.
We do that in the structural model, but the structural model will take skill, ability, everything into account in predicting what the outcome effect is. That's why I think the structural model really helps. But we saw this and we were like, oh my God, why is it not working the way that we thought? And then we realized when we ran the structural model that there was a really good reason this happened. So let me tell you what the model is, which is the really novel part, I think, of the paper. So here's the way we set it up. There are Q questions, and there's T bar times the amount of time. And you could either answer or not answer. And for each question, there are K choices. In this thing, there are 5 choices in this exam. And you have to choose one. And there's only one correct answer. There are not more than one. And for the correct answer, you get S points. In general, 1 point is the way to do it. And then for the wrong answer, you get S over K minus points. This is actually fair. And then you have a utility function, U of Y. And then how does the model work? The student is going to get a signal about each of the 5 options. And it's going to estimate the likelihood of each option being correct, defined by pi k. Okay? And pi c is the probability of choosing the correct answer. Let me just show you how this works. So what are you getting? You get a signal for each choice. So for question, answer A, this is the signal. Answer B, you get the signal. Answer C, D, E, you get these signals. Okay, so you have your 5 options. For each option, you get a signal. And you decide which option is most likely to be correct. Okay, that's our model in a nutshell. We have these signals drawn from a Pareto distribution. And the signals for the incorrect choice are drawn from alpha and I. This is the scale, this is the scale, and this is the shape. Alpha is the shape, and L is the scale. Now, the scale we set to be the same. That's where the cutoff is, right? Because we don't want ever for there to be certainty. If these scales were different, so if you were this was L1 and this was L2, right? If you got a signal over here, you'd know this was the distribution, right? So to prevent that, we make these L's the same. And with the Pareto distribution, right, you'll see that the reason we chose the Pareto distribution was when you write out the choice, intuitively, what are you doing? You're saying, oh, this in a way is giving me a signal for how good each answer is. Right? The higher the signal, the more likely it is that this is the correct answer. All right? When you look at that and you calculate the probability of choosing the correct answer using the Pareto distribution, you get this probability very simple. The trick here is a lot like what you do in Logit. You just use Bayes' rule repeatedly, and then you do some clever tricks with multiplying and dividing by the same variable, so things simplify. And this looks a lot like Logit. It's not Logit, but it gives you a very similar form. And this is what makes it easy to run this model and estimate things. So what happens, the intuition here, is you're going to be able to tell the difference between the right answer and the wrong answer if alpha and beta are very different. Of course, because you're getting a draw from these distributions for each of these A, B, C, D, E, right? If the correct answer is going to, so remember, the correct answer is drawn from beta, incorrect ones are drawn from alpha. Okay? If alpha and beta are very different, when you get a high Z, you say, that had to come from the correct answer. So I'm pretty certain of my answer, right? But if alpha and beta are very similar, then these distributions are almost on top of each other. And I really can't distinguish between the right answer and the wrong answer, right?
So one question, so IC doesn't depending on prior belief of these children.
So we're coming to what determines alpha. You'll see. What determines this difference alpha minus beta? That's what we're going to contribute.
So the IC is kind of posterior distribution of the student after getting signal.
Yes. So it's, you're getting this signal, you know, right? Depending on your ability, the difficulty of the question, and the time you have, this distribution will change. Alpha minus beta will change. That's the trick. Okay. So it's actually very intuitive, right? Because if, right, if you're not so bright, then you won't be able to distinguish between the right answer and the wrong answer. So for you, this alpha minus beta will be very low. That's all that we use this distribution for, these distributions for. Okay. Is that okay? So now the probability that it's correct will be the signal you got for the correct answer to the power alpha minus beta over the sum of all the signals to the power alpha minus beta. So this is his choice problem because we have a utility function. He's going to maximize his expected utility of answering versus the utility of not answering. So he will answer if this expected utility of answering is more than that of not answering, writing out what the expected utility is, right? This gives you just this, pi c more than this, and you can see that this is a measure of concavity. Because this is U naught to this, and this is US to US. Okay? So the more concave is U, the lower will be the denominator relative to the numerator, and the higher the right-hand side. So you can see very clearly that, whenever this probability correct is more than this cutoff, then you want to answer the question. So we call this tau the certainty cutoff, and that reflects confidence plus risk aversion. Confidence plus risk aversion because this utility function, curvature of it is fixed. But if you're going to behave differently, it's because of the confidence with more time. So, okay. And when we saw the probability correct, remember, only thing difference was alpha minus beta, not alpha and beta. If I move both the distributions to the right, but keep the alpha minus beta the same, it's as informative as if I didn't move all both distributions to the right. It's the difference between the signals for the correct one and the wrong one. That's all that matters for informativeness of the signal. So, we just say, okay, let's fix beta to be 1. And, alpha will be the Pareto shape for the incorrect answer distribution. And we're going to say alpha is going to be a function of ability, the proficiency of the student, the difficulty of the question, and the time that you get. Okay. So, as you get better, alpha is going to rise. Okay. As the question becomes more difficult, alpha is going to fall. As you get more time, alpha is going to rise. Beta is fixed, so that increase in alpha will increase this whole. How we take this G function and parameterize it, in many ways, was the hardest part of the paper, because it was very hard to get one that actually made sense. So I'll show you how we did this. So how did we measure ability and difficulty? We measured ability by using administrative data on practice exams, previous exams. We measured difficulty as usual, question fixed effects. How did we model alpha? This took us like 6 months to get right, okay? It's not that hard, but here's how we did it. So we have some scale parameters. So this is gamma naught as one scale to get the scale of alpha, right? Then this is sort of like a Cobb-Douglas, right? So ability, this is how important ability is. It's like the share alpha, the coefficient on one factor. So ability to the power gamma 1, difficulty to the power gamma 2, okay? And then time to the power gamma 3, and then this term is the trick. Because in order to match that hump-shaped treatment effect, what do you need? You need to be able to say that time will matter more for questions within reach, right? That's how this plays out. This is e to the power minus gamma 4, the absolute value of this difference between your ability and difficulty. So this is getting the within reach part. All right? So when the question is within reach, this will be almost 0, right? So e to the power 0 is 1. Then you'll get the full effect of time. If ability and difficulty are separated, you will get a smaller effect of time. So it took us too long to figure this form out, but it worked. The time, again, we had to scale. So there's some intercept, and then you're spending total time on the number of questions, and that's how we're measuring time. And this is able to capture what we saw in the data. You know it doesn't work when you think it should work, and then you get estimates which make no sense. Then you say, I'm an idiot, let me go back and figure out. So it took a long time to do this. So we estimate these parameters by gender, and the cutoff parameters are estimated separately by gender and treatment. So you get this cutoff for male, cutoff for female, and then for the control, and then for the treatment. And we'll see that these differ by gender and by treatment. Okay. And then, we estimate this by indirect inference. We match the moments in the simulated data to the actual data moments. And, the moments we're going to use are going to be for the two ability groups, low and high. We would have loved to have done this for more fine things, but data limitations. And given the fact that this is hump-shaped, you needed at least a 3-way classification for difficulty. Because if you have 2 points, you're only going to get a straight line up or a straight line down. To get a hump-shaped, you need 3 points at least. So we managed to take 48 questions and divide them into difficulty quintiles, 5 points. So, and we simulate the fraction correct and skipped by ability cross difficulty cross treatment. And those are our ones. estimation procedure is very standard. Take the vector of parameter values, simulate the model, get the generated data, use the difference between the model data and the actual data, weighing matrix, start with the identity matrix and then go to the optimal matrix. And you want to basically minimize this loss function. And we start with local maximize and get to the global. Okay, so straightforward. Okay, here's what we get for estimates. And our estimates are, this is, again, we have the p-values. And what's really interesting is, so men and women have very different proficiency rates. So ability matters differently for men and women in the signal production function. It matters more for women than for men. Difficulty, again, matters more for women than for men. It's not just chance. Time matters more for men than women. This is why the men are gaining more for more time. Okay? And this discrepancy factor, that's just getting things to line. So these two are less important. Certainty cutoff, the control, for men, it was 0.335. For women, it was 0.345. This could be chance. For the treatment, again, could be chance. So you can't say that men and women are different in terms of their certainty factor. It's the production function that's different.
Sorry, explain again what is the weight here? Because
Sorry?
What is the weight again? Like, could you explain what you
the efficiency weight, it's the coefficient on ability. The scaling was to get everything lined up. Because, how do you know you got the right scaling for these things? So we had to allow, we said we need to allow for these things to be sure that we got this right. So this is what made us decide. People may have been misinterpreting the data because they didn't look at the data through the lens of a model. When you look at the data through the lens of the model, you say, this is not where the difference is between men and women. The difference is really in how they take, how they get information from the signals that they're getting, depending on their ability, the time, and the difficulty of the question. So, I don't know whether the psychologists are going to love this or not, but for an economist, I think it makes sense. Why should women be thinking about things the same way as men? We've seen many places where they don't, and this seems to be another one. So this is just what we find. Now, in all these estimates, you always have to make sure you have identification, right? How do you do that? You look at each parameter and you look at each moment. And you make sure that for each parameter, there's some dark moment. Dark means a high elasticity. The elasticity between this and this moment. That as you change, right, the moment, the parameter. So these things these are for the 5 quintiles that you have. So this is the fraction correct, right? For the low and high group, and for the treatment and control. So C is the control, T is the treatment. So this is the fraction correct for the low ability group in the control. And these are the 5 different question difficulty quintiles. Okay, so and these are the elasticities of that moment to the here. So you see, it's the fifth one that's the most responsive here. Do you see what I'm saying? So that's how we've shown this. Basically, you want to make sure that for each parameter, there's some dark blue somewhere. So we have a lot of moments.
So the question delta 4 doesn't affect much. No.
Yeah. So some are stronger than the others. So gamma 4,
Gamma
it's,
4 might
you know,
be
there's something that's dark. Yeah, it's not light all the way. And you see sometimes it's completely light. So gamma 4 is one which what we call a khichdi. There's no one moment which is doing it, but there's enough color in the third layer that it works.
Okay.
So this is a very nice way of, I think, showing that there's something there and what is there, what is doing it.
And the gamma 0 and the gamma 2 moves the same direction.
Sorry, gamma 2?
Gamma 2 and gamma 0. So it's like the same.
Yeah, it seems the same sort of moments are identifying both. That's absolutely correct.
No, can you separately identify this? Because
They separately identify because the elasticity of that parameter to all the moments. They're separately identified. You don't have to worry about the same moment helping in many things, because the elasticity is for this parameter with respect to each of these 5 moments.
The gamma 0 and the gamma 2 have a very similar color.
Yes, but it doesn't matter. It's not exactly the same. The colors are a little different. It's not the same numbers. Yeah. You don't have to worry about these patterns looking like good here. All you have to worry about is for every parameter, there's some dark color. This is sort of, I think, the standard way of showing that things are identified these days. This comes from the Cooper, Ada Cooper book, actually. That's the first place I saw it being used. So this is identification. This is just model fit. You can see these are pretty good. This is a little bit off, but good enough. This is just showing that the model fits the data quite well in terms of predicting for time per question. So the X's are the experiment data. The blue one is the male, and the pink one is the female. Pink and blue, male, female, easier to remember. You can see that the model and the experiment in the 2 places where their times are the same are pretty much lining up perfectly. Right? And you see the model will let you predict not just these 2 points, but all the points for all times. This is, the advantages of the structural models. So, you see fits the data, we will skip more and get fewer correct. And this is what you just see in the picture. You're skipping more, getting fewer correct. For low ability, this is low ability group and high ability group. What you're seeing more time is increasing the fraction correct more for within reach questions. Right? Low ability, there's more difference here. Right? And high ability, but it's there more for the more difficult questions. Okay. Again, what you were expecting. I think this is sort of where we actually have something more to say, which is how do we design the exam to help sort students? And the intuition is very straightforward. Let's look at the difficulty distribution in the green thing and the ability distribution in the purple thing. Okay? When the difficulty is matched with the ability, then you get good sorting. When the difficulty is not matched with the ability, you get bad sorting. Here in this picture, what do you see? You see that on the bottom of the ability distribution, you will get good sorting. But the questions are too easy. Questions are easy. You won't get good sorting at the top of the ability distribution. The opposite is clear here. You'll get good sorting at the top because the questions are difficult. When this is on top of it, then you'll get good sorting everywhere. Right? So if you have the SAT, you need an exam which will cover the entire spectrum because you want to know all of the students, to sort all of the students. But if you're looking at the AMT, which you're targeting the top students, you need this kind of an exam, one which will really be extreme to sort only the best, right, students. So depending on what you want to sort, you'll have a different exam. That's obvious, right? So these are a little scary, but it's actually very straightforward. This is all students together. Okay. Here, we have exam difficulty on the y-axis and population proficiency on the x-axis. We can take our estimated model and simulate it and see how well it's sorting. Okay. So, what are you seeing? There's like a sweet spot, okay, from our picture. As you change the pressure from low pressure to medium pressure to high pressure, you're getting better and better sorting. Why? When there's low pressure, people are guessing, right? This is difficulty, and this is low ability students. The low ability students are guessing. You can't sort them well, even when the questions are quite difficult, because you're giving them a huge amount of time. As you start making the pressure higher by giving them less and less time, you're able to sort these people where you couldn't sort them here. Because less time, high pressure, is like increasing question difficulty. And remember, you can only sort them when the difficulty is high or the pressure is high. So this is sort of, the pictures are showing that there's a band here. Sometimes you only see part of the band. You only see the top part of the band. You don't see, so you have, really the band is like this. You're not sorting here so well. You're not sorting here so well, right? You're sorting in between. Okay? As you change the pressure, you see what's happening. The band is moving from here in the middle to higher, to highest. You've lost the top. But if I'd made this thing bigger, right? If I'd gotten 10 higher and made this scale more variation, I would have seen this yellow part here on the top there. So that's the best way I found to think of it, as a band in the middle. And as you change the pressure, it's like making it more difficult, and where the band is working changes. So it's a lot like the picture we had earlier. Here. As you change the difficulty, whom you're sorting changes. So it's the same idea, but in 3 dimensions. But what do I want you to get from you here? Here, this is when you take everyone and sort them all together. Here, you're sorting men with men and women with women. How do you do this? Supposing you have 100 seats and there's 60% of the population is men. You keep 60% of the seats for men, and then you sort the men into those 60% seats. And the 40% women will get the 40% seats, and you sort the women among the women. Note, look at what's happening. The yellow part is smaller. Sorting is much better when you sort women with women and men with men. Why? This is obvious. Their production functions are different. Their signal processing functions are different. So if you sort them all together, you're mixing it up. Their signal processing functions are different, and you're trying to sort them together. This doesn't make any sense. So this is the first non-affirmative action type reason for something that looks like affirmative action. It's not affirmative action, because we're not saying give women an advantage to men. We're just saying women are different from men. So sort the women with the women and the men with the men. You'll get better sorting. This is one of the big messages, I think, of this paper, which is when you use the model to understand the data, you see what we thought was true earlier is actually not quite true. And that means that to sort people well, you need to account for the reason why we're getting this false result, which is that men and women are different in the way that they're processing the signal. So we're very close to done. Adaptive testing may help in sorting. We don't do this here, but.
So when you design an exam, so you can change the time for exam and difficulty of questions. At the same time, you could also change the amount of penalty for wrong answer.
Oh, we have that also. You'll see. We did that. The penalty does the same thing. So here we go. These are, when you have different penalties, no penalty, penalty of 0.5, and an even higher penalty. And the effects are exactly what you would expect. It's hard to sort low ability students when there's no penalty for guessing. They'll just guess. And so you're going to get a lot of noise. And that's going to really hurt sorting, especially in the low pressure, which is what you see. Yellow, yellow, low pressure. As pressure goes up, it goes away a little bit. Okay? The higher penalty reduces this guessing, which improves sorting. But as the penalty rises, so does skipping, which hurts sorting. So you're getting less clear things here. Yeah. Here you couldn't sort, you're sorting a little bit better here. Maybe a little bit better here. But here, too much penalty, you're again going off. So this is the penalty thing. So, that's basically what we have to say. Our contribution is the structural model with the experiment. And in many ways, I think this is the combination of an experiment and a structural model is a great way to get the pluses of both. The experiment lets you not have to worry about all the econometric issues that are there in real world data. And the structural model lets you go to understand what's behind the data that you've got with your experiment. And we're seeing very clearly that time pressure will not affect all students the same way. And the counterfactuals are going to tell you about how to design a better exam in terms of negative marking, time pressure, question difficulty for the object that you have, which is sorting all students, getting certification, or trying to get, say, the best, very best students. You would have a very different exam for all of them. So that's all I have to say. Thank you very much. Thank you very much. Thank you. Thank you for listening for so long.
I was wondering whether this is nature or nurture. This is Turkey, and the Muslim country, and gender segmentation is very clear.
That's a very good
So
question.
maybe Christian community or developed economies.
I mean, if you could,
I don't know.
you could run this on cultures which are very different, right? You could run this on like Turkish East and West. The West is much more liberal than the East. It's very conservative in the East. It would be interesting to see
That's right.
what the model says is different. There's so much you can do with this. You know, you could just run the same experiment in different places and pick up the effects of these cultures. What is happening?
So one thing I was impressed by your research is that even though the sample size is very small, like 90 students,
It works. No.
It works.
Yeah,
So-
I'm shocked.
Why is that? So, because when I design RCT type of study, usually we need a few hundreds of individual in control and treatment.
I think the reason is because you have, when you do an RCT, you're model free. So you can't use the model, which makes sense, to help you identify things. Here, you're using the best of both.
I see.
The RCT is removing all the econometric problems that kill you.
I see.
Right?
Particularly endogeneity.
Exactly.
You still have
Selective.
to take the information from the model that reduces the
Exactly. Exactly. And that helps you zoom in if you have the right model. But you have to be very careful that the model is capable of picking up what's in the data when you estimate it. If you don't have that ability, you'll get garbage. And we know that because, before we figured out how to allow the parametric form, to get the parametric form right, so it was not getting results by assumption. We were getting garbage. It looks so simple, but it was really hard for us to get the right, form. But it was again, a lot of fun. I learned a lot.
Even with a simple comparison between treatment and control, you can detect there are small difference.
You see the differences it's so clearly there.
Did you control for some observed characteristics before running the experiment? Even without
completely
control?
randomized
Okay.
between the students with us. So, it was very straightforward. But I think this paper shows the strengths of each can be harnessed for the other. At least that's how I see it.
Sorry. Thank you.
Thank you very much.